This might be this might not be possible, but what I'm trying to do is I'm trying to uh, build a QFT without the swap operations, right? So, and I want to basically in this short intro video, I want to kind of give you a run through what I've tried and my thoughts. So I tried in the past. I try to basically do a bunch of stuff here in terms of playing with no, I didn't bookmark that, I think, but you can check out the previous videos playing with controlled operations. But then I kind of realized that if you have two registers, right, like let's imagine you're having simply one register down here that's used for the input, another one that's used for the output, and then you're using controlled operations. When you're gonna try to run the inverse of the QFT or whatever, like when you've got a superposition here, that's definitely gonna create a nasty entanglement that's not gonna let you really get that to work, or not. At least I don't know how, so I don't know. But now I'm trying something else, which it's an idea that came from taking a look at third, I think it was, but no. So I think uh, there are a couple of Fourier building your own quantum Fourier transform. So there was one sentence in here. I haven't read this through at all, but like I saw this animation which is really nice, and basically, um, so one of the things that I realized here is that the essence of the Hadamard is, I mean, the algorithm is using the Hadamard to basically detect and compress patterns, right? So if you've got, forget about the bottom one, so if you got the top register here, and this is just input preparation, okay? So I'm just preparing like something, and then I want to kind of revert it back with the inverse QFT, so I get like the 0, 1, 0 as an outcome here, right? So which I get in here, right? And so what's happening here, if you pay attention to the Hadamard gate being applied at this qubit, right, is that it's gonna try to detect whether there's a pattern between these four values and these four values. And so if this matches, right, like you can see that the phases are the same, then it's gonna compress it and basically pack it into the part of your amplitude elements that start at zero. The reason for that is that if you remember, the Hadamard operation takes basically the state 0 to the state plus and vice versa as well. So in this case, a plus state is state where the phase of uh, the relative phase between 0 and 1 is the same, right? If there was a 1 in here, no, how can I have an example where there's like, oh, this is an example, right? So here you can see that the two patterns are mirrored, are the opposite, right? So you've got like phase 0 is phase 180 degrees, phase 45, and this is phase 135. So then it will basically pack those, but then pack them into the bottom half of the rectangle here. That's basically the ones that have the 1 for that qubit, because if you remember, the Hadamard takes you to the minus state in this case, and vice versa, and the minus state is 0, minus 1. So, I mean, you can intuitively interpret that as saying if the relative phase of your set of states is sort of mirrored, like here's a plus and here's a minus, then that's how you can compress it, right? So that's why this is happening this way. The the problem So now this is what I want to refine in the next videos, right? The problem is that I think that this behavior basically causes uh, the beats to, or causes some of the beats to flip, right? In this case, to swap, to get swapped. So it's sort of a not undesired effect. I think here's basically the problem is that doing QFT has a tendency to reverse our qubits, right? Exactly. And this is because of the Hadamards. So yeah, and so basically, usually you apply the swap gates to correct it, but I thought, um, is there any other way to do that, right? I mean, I kind of come to accept the fact that, okay, this is okay with me. It's like it's the effect the Hadamards have because they compress the patterns in that way. But I want to get a bit deeper into this right now. But then my idea would be: is there a way to implement a kind of Hadamard operation that does that compressing pattern that we want, but doesn't create or have that side effect of swapping the qubits? Um, so sort of a custom gate in this case that exhibits the same features that we want but doesn't exhibit the one that we don't want. So basically, I'd say, I'll be trying in the next videos to design a gate that um, is sort of a pattern recognition and pattern compression gate. You can see it this way, right? Like the same. It's kind of what the Hadamard is doing, really. Um, And if that's possible, because I don't know if that's possible at all, then it would mean that we can actually use that to create a Hadamard, a QFT that doesn't have that effect. Now, trying to understand what's the pattern here, right? Because so here I'm playing in the bottom register. I've been playing with some gates. I call them D, just because my name is Daniel. D4 is sort of my fourth attempt. I'm trying to kind of see whether I can do something similar where I do this in here, right? And basically, as you can see, and the next step, it's kind of getting the same that you have here, but on the top instead of the bottom, which was my first thought, as in like maybe that's what we should do, right? Here, yeah. Then obviously those control nodes must be like the empty circle for the X, because you're going to have that part empty, so it's going to be a 0. The first qubit is going to be for sure a 0 in this case, right? Yeah. But I don't know, try to keep the rotations, so after the rotation you're getting to the same which you would have after this rotation. So this is the same like you have here, right? And then you would apply another D4 gate in here, and so you would basically have in here the same what you have here, but this is where things don't work as I expected them to work, because I would like this pattern to be compressed here. Okay. Which is not true. That's completely not true. For that input, we want to get 111, because that's what we want to get. So this is already wrong from the very beginning. So that works well. I think the D4 gate works well when the input is 1, at least in my latest test. So, but it's basically, so if I do these and I clean some of this stuff and I put it in here, d4, 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 and then I apply a last d4. It doesn't work. It's 0, 1, 1. Okay, it should be 0, 0, 0, 0, 1. So it's also not. It should be these. So that also doesn't work. Does it work for 0, for 2? That kind of, no, also doesn't work. So, but you see what I'm trying to do, right? So it's definitely, d4 is definitely not. I was just playing intuitively with making gates like, you know, something like x minus z, and then, you know, 180 degrees and some stuff like, sort of like something similar to what the Hadamard gate does, but without really giving it a deep thought. So that's my my first step. But maybe what I should do is I should step back for a second and think through that a bit more and try to understand what the Hadamard is really doing and what I want then to happen. What's the behavior that I want to correct? So where is the swap happening exactly? So that's the maybe that's the best way to approach it. So take a look at the Hadamard version of the QFT, right? And then see where is the, is it really because of the Hadamards? You know, it's like, where is the actual problem appearing, right? Because let's do the following. Let's get rid of the bottom part and let's simply analyze the QFT. Maybe I'll do it with maybe we should do it with 4 qubits, because then we gotta apply. No, let's keep it at 3 qubits because we only have to apply 1 swap. So basically that's still my input preparation, right? So this we don't care about. That's what we got, and we want to get 0, 1, 0. Let's choose an input where the actual swap matters, right? So we want to get 0, 0, 1 at the end. That's step preparation, input preparation. So we've got this thing here, and the first thing that happens is pay attention that if we want 0, 0, 1, it means our final amplitude, our final possible state, like our final state, must be somewhere up here, right? And so the Hadamard is, this Hadamard is already messing it up because it's basically removing that. So that's kind of already introducing. In this case, we've already messed it up. So it's like, oh, now you got now you'll have to swap. Does this happen when these numbers are different? Like if I have like these, for example, right? The Hadamards are not spoiling anything really, right? Because this always, exactly. So it happens only for, and if I have like something like 0, 0, 0, that also doesn't get spoiled, and if I have 0 and 0, that also never gets spoiled. Okay, interesting. So that happens whenever the, okay, so we know what inputs are causing these to have to, the inputs that are causing these are the inputs that have the those qubits different, right? Because if they are the same, then the Hadamards seem to work correctly. So that's just the correction for that, and that particular correction doesn't affect the states when they are equal, because basically they're equal. So that's why it doesn't really affect it. it would affect, but it doesn't, right? Because it's a swap and the values are the same. Interesting. So that tells me that we could maybe. So you gotta be careful because that's a feature of this whatever custom gate that needs to be preserved somehow. But why is that? So you've got 0 and 0, right? So why is that? You've got that pattern, and so now this pattern is if these numbers are if these numbers are different, right? No, if they are the same, then they are mirrored. Are they? No, because now this is the same. So this has nothing to do with being mirrored or not being mirrored. Yeah. This has to do with where we want the final state to end up. So this doesn't really... Okay, so there's no relation between the party of these, I would say. I mean, party. I don't know if you can calculate that with party, but has nothing to do with this. Okay, so but let's then stick to the case where we've got these. So, and if I have a 1 here, then that just those things stay mirrored, but that again doesn't really affect. Okay. So the Hadamard would basically catch whatever pattern and pack it in here, whether they are mirrored or not. That's the pattern. I think that's basically the first case. Important pattern present in the inputs. Look at the amplitudes for the states that are 4 apart. Yeah. So here these amplitudes are mirrored, right? You see it after 4 turns of I divided by A, the resulting state is always exactly equal or exactly opposite. Why is that useful? Because a Hadamard gate will factor out that pattern. It has exactly the same sort of regularity. Inserting the Hadamard gate on QB2 and the pattern is 4 apart will make things simpler. The above animation is showing that a Hadamard gate on bit 2 gets us closer to our goal. We want each input frequency to end up as a single output. And after the Hadamard gate, they are in 4 states instead of 8, halfway there. It's tempting to try to apply the same trick to B1, but it doesn't quite work. Do you see the problem? Although the top rows have the opposite or equal property, but spaced by 2 instead of 4, the bottom 4 rows don't. The bottom 2 are off by 90 degrees. The bottom 2 rows are at offset 6 and 7, which is here are the states where bit 1 and bit 2 are both on. We want to make the faces of these states rotate by 90 degrees. Phase shift gate almost does what we want, but it's only conditional on a single bit. We make it conditional on both by setting the other bits wire as a control for the operation. Condition on the single bit. Put a right gate on bit 1 will factor out another half the chunk. Another part is clear for what needs to be done for the last beat. We'll use a phase shift gate to ensure that the remaining non-empty states in each column have equal. We want a nice diagonal line, but right now things look more like a circle. The problem is that doing QFT has a tendency to reverse our bits. course, it's not the only solution. For example, you could also swap the beats beforehand, a slight rearrangement of the gates, and you get the circuit and you get the circuit I used for the QFT animation from last time. You might worry that because only test a single frequencies, fortunately current circuits are implemented in your operations. This means scaling an input will scale the output, and adding inputs will add outputs. Handling combinations of inputs is a free built-in functionality.